All right, folks, welcome to C321. And we were talking about roadway design. So we're going to continue that discussion a little bit. And we were talking about horizontal curves. We talked about this problem where we learned to do the stationing of an horizontal curve. Remember, when you're looking at horizontal curves, you're looking at top view, and then you have to measure these stationing along the alignments, right? So we talked about how if you know the stationing of PI, you need to subtract the tangent length and get the stationing of PC. And then you can get any point on this curve, including the PT, by adding to the stationing of PC the circular curve arc length, right? And we learned the formula to estimate that arc length, the degree, the measurement of the angles in degree versus radian, and how that gets used in estimating of the curve's arc length. So that's basically, important things. And one of the things that will happen in your homework problem that I've assigned to you is that you'll have to make use of those relationships. For example, all of these equations, all of these trigonometric equations that you're going to have to make use of. And these are like, basic trigonometry equation. There's not much fancy things going on as long as you know how to define the sine and the cosine of a right angle triangle in a right angle triangle of an angle. You should be good to go. But just kind of remember to use these formulas and kind of think about those problems in that context. The next thing I want to talk about is this idea of superelevation, right? So superelevation is the third element of design. So we've talked about two different elements so far. We've talked about the vertical alignment first, where you're looking at the profile view and how roadway goes up the grade and then down the grade as you travel along the roadway. Then there is the top view, where you talk about the change in direction, right? So that's your horizontal alignment. But this one, the last one, the superelevation, it's part of the cross-sectional alignment, or it's the cross-section of the roadway, okay? So there, you are looking at a roadway section, the road that goes in and out of the plane of the board, right? So if you're looking at a typical roadway, the typical roadway goes like this, right? So you raise the outer edge of the roadway a little bit, and this grade is typically about 2%. And what you're looking for here is the cross section of the road. Okay, so this is the width of the road. So maybe there is a lane here. So this is the lane divider. Maybe this is the center line of the roadway going into the plane of the board. And then this grade is about, in general, on straight segments, this will be something like a 2% grade. Okay, a 2% grade. And we call it the cross-section grade or cross-section of the roadway. And this type of a grade is provided so that when the water falls, if there is a rain event or whatever, the water sort of drains to the side of the roadway and does not damage the pavement. Okay, so the cross-section design typically will be this, we call it 2%, and then this will be like one direction. And typical sections are these crown sections, right? So if you look at any roadway like that, that's going into two sides, the roadway will be like this. So let's say there is two lanes in each direction. So there'll be like this lane going into the plane of the board, again into the plane of the board, and then coming out of the plane of the board. So this roadway is going this way. And then this is what we call it'll have like a 2% cross-section flow on both directions. And this is what we call a typical crown section. A crown section. Now, what happens is that, and we don't provide a very large slope for these crown section because we just want the water to drain, and 2% grade is typically sufficient for the water that falls on the roadway during rain events just kind of go onto the side and not accumulate on the roadway itself, on the pavement itself. Now, what happens when you enter a horizontal curve? When you enter a horizontal curve, what happens is this crown section is not sufficient for us. It doesn't quite work for us. And the reason for that is that when your roadway is on a horizontal curve, right? So if you look at the top view of a roadway, the top view looks something like this, where the roadway is turning like this, right? So you're changing your direction of travel from here to here like this. When this is happening, think about a car traveling on this on this section here. And as car travels on it, let's say the car is traveling at 60 miles an hour. Or let's just say it's traveling at 60 miles an hour. Let me ask you this. Does that car traveling on this segment does it have any acceleration? Yes or no? Right? Its speed is not changing in magnitude. So there is no change in speed or change in speed, but there is certainly change in the velocity vector, right? So if you think about scalar versus vector, the scalar speed is constant at 60 miles an hour or whatever speed you're traveling at. So if you're traveling at the straight segment of this curve, and let's say this is PC, the point of curvature. So when you're traveling at 60 miles an hour on the straight segment, there is no acceleration. You're traveling at that same. So all your balances, all your forces on that, are balanced. But once you enter the curvature or curved section of the roadway, now you do have an acceleration. And that acceleration is what's keeping you on that curved path, right? So you need basically what you need to travel on a curved section of the roadway to be on that, to be able to maintain yourself on that section, curved section, you require a force inward that pulls you inward. So you have a net acceleration, is what I'm trying to say. Does that make sense? Right? If you're trying to travel on this curved section, you require a force pulling you inward so that you remain on that section. Okay? Now, to be able to do this, right? So to be able to do this, so on a curved section, that's why this crown section doesn't work. Sometimes you require more than 2% slope. So what you will find is on a horizontal curve like this, you don't provide a crown section, but instead you provide a super elevated section. So this is a section that's super elevated, and this is the center line of the road. And then, you raise the outer edge of the pavement, and then, the curve is going this way. You raise the outer edge of the pavement. So this is the outer edge, and this is the inner edge. And you raise the outer edge of the roadway so that you're providing a force inward for your curvature, for being, so that, there is a gravitational pull that takes you inward and you're able to maintain your path as a driver, or it makes it easier for you to maintain that path. Now, if you're talking about what that slope looks like, in urban areas, we cap it at 6%, right? So in urban roadways, if I have to provide a super elevation, I will cap that super elevation at 6%. Or if I'm talking about a rural area where the speeds are a little bit higher and congestion is less expected, I will say I cap it at about 8%. So the outer edge is only raised to about 6% grade or an 8% grade, depending upon the surrounding land use. Now, the thing about these super elevated sections is that you probably have seen super elevation. So what happens is that this force that you require is the net force that you require to be able to maintain on this path is given as m v square over r. Okay, so this is sort of is the typical definition of the force that your net force that you require if you're traveling on a circular path with radius r and you're traveling at a constant scalar speed of v, right? And the mass of the vehicle is m. So then you require a force that's mv squared over r, right? So that's the net acceleration that you need to travel on a circular path, mv squared over r. And that comes from physics. But if you think about this force here, it's proportional to the square of speed, and it's inversely proportional to the radius, right? So shorter the radius, that means tighter the curve, you require more force inward, right? And higher the speed, you require more force inward, right? Now, thinking about super elevation to make it clear what that is. Have you guys, I mean, on the roadway, right? If you're talking about a, Caltrans maintained state highway, even that has 70 miles an hour speed. If you look at it from a naked eye, a rural area, even at, let's say it has 8% super elevation, you'll probably have a hard time making out that, yes, does this look like an 8%? The outer edge is raised compared to the inner edge. You'll have a hard time locating that. But you could probably think of a situation where the speeds are high and the radius is tight, where it's very easy to make out these super elevated sections. You can actually see it with your naked eye. Can you remember what that context might be? Have you seen the NASCAR tracks, right? Those racing tracks, you can clearly see that the outer edge is much, much higher than the inner edge, right? Why is that? Basically, that's providing that super elevated section. And we have to do the same thing on our roadways, but hopefully nobody's driving, I don't know, 180 miles an hour or whatever they drive at, right? So yeah, that's the idea. It's the same idea why the NASCAR track is raised. It's the same idea why we provide super elevated section. It's just that our super elevations in roadway design are not as pronounced as they would be on a NASCAR track. Okay, so now if you want to find out how much super elevation you need to provide, this is your governing equation right here. Okay, tangent alpha is that grade. So this 8% or 6%, that's represented by tangent alpha of this angle. So this is alpha. So tangent alpha represents that grade. And then our grade, as I said, is going to be 6% to 8%. Fs is the coefficient of side friction. What is the friction for the car to move sideways? Okay, what's the friction coefficient between the tire and the pavement surface for the sideward movement? Okay, so that's your Fs. Fs is the coefficient of side friction. Okay, V square over GRV. V stands for the speed. Okay, G is the gravitational acceleration constant, G. So this is your gravity acceleration constant. And RV. So RV represents radius, but we put that subscript V in there to denote that when you're designing a roadway, because remember I said this force depends on the radius. So think about a 2-lane road or a 4-lane road or whatever. This force that you need will vary depending upon which lane you're in, right? If you're talking about the outside lane, would that have a larger radius or a smaller radius? If you're talking about the outside lane, it would have a larger radius. But talking about the inside lane, that will have much shorter radius, right? Because the radius will be reduced by the width of the roadway. That makes sense? Like however much your radius is on the outside, your roadway width will impact what kind of impact you will have, right? Or what kind of acceleration you're going to need. So that's why we put like this. We always want to analyze the need for super elevation based on the critical radius, RV, and that's the inside radius. And every time I teach this class, I say to myself, I'm going to go look up, why do they put the subscript V in there? And every time I forget, I'm going to do that this time. Okay, because now I'm on record, right? So this time I'm recording this. So I'm going to be on record. I'm going to look that up, why they came up with the subscript V. But subscript V is there to denote that you're not talking about the radius of the curve from the center line of the roadway, but you're talking about the radius of the curve as measured from the critical inside lane of the roadway. That makes sense? So that's why you have an R sub V in there. If I had to guess, again, maybe I'm making a fool of myself here, but if I had to guess, it's V is like some German term for the inner lane or something. I don't know, but we'll have to think about it. I'll have to look that up, I guess. Okay, so that's your RV. G is like, the gravitational acceleration constant, so 32.2 feet per second squared. We already mentioned the Fs value, which is the coefficient of side friction, and tangent alpha is the super elevation for the cross section of the road. Okay. So when you do all of this, and I'm showing you the movement of a road movement of a car, on the inside lane. So I'm just showing you that movement there. And then you can balance the forces, but then this is the equation you're going to end up with. Tan alpha plus Fs equal to V square over GRV times 1 minus Fs tangent alpha. Now, if you look at that equation, we can find this super elevation E value and the Fs value for horizontal curve on the AASHTO Green Book. And this is from an older version of the AASHTO Green Book, but the tables remain pretty largely the same here. Now, one thing that you have to think about is that I said that we limit the super elevation to 6% in urban areas and 8% in rural areas. And why do we limit that? Because what happens is that if you provide that super elevated section, and for whatever reason, drivers cannot actually travel at the design speed or are having to travel much, much lower than the design speed, then they will have a hard time navigating that curve, because now the acceleration that was there to supposed to be balancing the force that you require to travel this section at a speed v. If your speed is low, then that required force becomes much lower. And now that super elevation is going to start to pull you inward. And then you're going to have some steering problems, kind of be able to maintain that path. So what you want to have happen is not have super elevation so large that if for whatever reason, if you have to go slower on that segment, and then the drivers are having steering issues. So that's why we limit how much super elevation we want to provide. And then so that anytime the drivers have to go slow on that segment, they can still travel slowly. But then if they're traveling fast, they have enough, inward force to kind of keep them on that curve. Okay. And again, as I said, it's all based on what's happening when you travel on the inside lane along the curve. So that's the other thing, right? So if you're talking about, so what's the implication in real world, right? So if you are thinking about, if you're driving on a roadway, let's say 101 or whatever, and you see a curve coming into it. So if you can be on the outside lane, you can drive a little bit faster on the outside lane compared to the inside lane, because the inside lane, it's going to be a tighter curve. So that's kind of the idea there, is that outer curve will give you a little bit more radius. So you can drive a little bit faster on that lane. So let's look at this number here. A roadway is being designed for a speed of 70 miles per hour. At one horizontal curve, it's known that the super elevation is 0.08 and coefficient of friction is 0.10. Determine the minimum radius of curve that will provide for safe vehicle operation. So let me go back to this formula here that I showed you before. Paste this formula right here for a second. Okay, so this is your formula that you're going to use to determine what force you need. Now, if you look at this formula does not have, it doesn't account for the units, right? So basically, you have to put everything in the same units for this formula to work, right? So tangent alpha, I told you, is the super elevation. So let's figure out, let's go through this equation and see if we know everything in this equation, or if there are some things that we don't know yet. So let's see if we do I know tangent alpha here? So let's see. I want to try to see if I know. Do I know tangent alpha? Yeah. What is that? 0.08. Right? 0.08. Right? So tangent alpha is 0.08, right? Because that's the super elevation. I told you this is now, one property of this tangent alpha, though, is if you remember, again, maybe, I don't know where you learn it, maybe somewhere when you learn the limits. If you're talking about small angles, like 8%, 6%, 4%, like that, at that value, the difference between alpha and tangent alpha is very, very small. But you can treat alpha as tangent alpha. They're basically the same value. But let's just say the tangent alpha is given to us as 0.08. Coefficient of side friction, Fs, is that known in this problem? Right? They give you that directly, so 0.10, that's good. So Fs is given to us as well. We know the first two terms. Let's come to the right-hand side of the equation. The speed is 70 miles an hour, right? So what's the value for V that I should put in? V is equal to 70. For now, I think I'm fine. I can put 70 is fine, right? So V is 70 miles an hour. So that's what I'm going to live with for now. But let's look at the next term. The next term I need is G, small g. And you might remember that from physics, what that value looks like. Remember that? 9.81, but that's metric units. So that's your 9.81 meter per second squared, right? But we don't deal with the metric system here, at least in the roadway design part of the curriculum. We are always dealing with the English units, imperial units. So tell me, do you remember the G value from imperial units? 32.2 feet per second square. Now I have a problem, because now I have my speed is in miles per hour, but I remember my G value in 32.2 feet per second square. Now I have a problem. So then what I need to do is I need to kind of write that V also in feet per second, right? So that my units are in good shape. So I'll say All right. So give me, so one thing is that, so 70 miles an hour. So you convert that by using 70 times miles into feet. What's the miles into feet conversion? 50 to 80, right? So 50 to 80, 5,280 feet. Oh, not 4,000, 5,280 feet. And then what's the hours to second conversion? 3,600. 1 hour has 3,600 seconds. So okay, 70 times 50 to 80 divided by 3,600. Now, one thing that might be helpful to you when you're in a time crunch and trying to solve these problems is that remember what this ratio is. 50 to 80 divided by 3,600. So that ratio is about 1.47. Okay, so I'm going to say this is my units, feet per second. So that ratio is 70 times 1.47. So that remembering this ratio might be helpful to you guys. That anytime I want to convert a speed in miles per hour into feet per second, this ratio is 1.47. Okay, it's kind of knowing that might be helpful. Okay, so we got G now, and then 70 times 1.47 feet per second. So I'm good with that. Let's see. RV. Do I know RV or R in this example? The radius that they're asking for, the minimum radius of the curve that will provide for safe vehicle operation. That's what they're asking. So I'm going to leave RV as it is. But now, once I solve the equation, what would my RV look like? RV, what would be the units of RV that I'm going to get from this? Feet, right? Because I converted everything into feet per second. I had miles per hour. I converted that to feet per second. And these were unitless, so I'm good with that. So I'm going to get my answer in feet. The R is the unknown. And then 1 minus FS10 alpha. So I know both of those values as well. Okay. So you can go ahead and basically plug the numbers and find the answer because all you're looking for is R in this equation or the critical radius in this equation. So you can go ahead and solve this. Now, one thing I want you to do is I want to half the class to solve for just this equation. Just use this equation as, so all I want you to do is, so you guys can solve the full equation. So up to this row, maybe up to this row here, you guys can all solve the full equation. Okay, so you can get started on that. And then for this part of the class, what I want you guys to do is forget about this part even existing. Forget about, ignore all of this 1 minus tangent alpha thing. Okay, just solve tangent alpha plus Fs equal to V square over GR. Okay, so the rest of the class, just ignore this piece right here and just solve tangent alpha plus Fs equal to V square over GRV. Okay, and I want to get the two answers from R. So let's write down two answers here. Find the exact answer for R. And then I want to find R approximate. Hopefully. So tell me if you have the exact answer for R, anybody from this side. All right. So R exact, anybody?
1,812.
1,812 feet. That's good. Does anybody have R approximate? Could be an easier calculation. 1826 feet.
27.
27. All right. Not that different, but so one thing about these is that I got R exact value. If I apply the full equation that I showed you in the slide there, if you apply the full equation, you get the answer to be 1,812 feet. Okay. But if you don't apply that, if you ignore this part, Fs tan alpha, you get pretty close answers. It's not a, in the scheme of things, in a curve that is 1800 feet or longer, that's such a large curve, you don't get a big difference between the two radius. And then the critical radius, if you use the approximate formula, comes out to be larger. It's a little bit more of a conservative value because you're providing a larger curve, the 1827 feet. Okay, it comes out a little bit larger, but very close, right? So what you will see in roadway design sometimes is people just use tangent alpha plus Fs equal to V square over GRV as your equation. Why? Because what happens is that this term, because Fs is in the range of like 0.1 or 0.008 or 0.08 and so forth, right? And then when you multiply that by super elevation rate, which is 0.08 is basically the maximum value that you can have in a rural area. And typically that value is also lower than this, right? So when you multiply two small numbers like Fs multiplied by tangent alpha, what happens? That multiplication becomes even smaller, right? And you can ignore it with respect to 1.0. So even in this example, what's the multiplication? It's 0.008. So 0.1 times 0.08 is a very small number compared to 1.0. Okay, so that's why it doesn't make a big difference in the calculation of things. So in roadway design, often this multiplication, this whole thing could be ignored because 1 minus Fs tangent alpha is basically equal to 1.0. It's very close to 1.0. Okay, so it's okay if you do it either calculation. If you want to do the full calculation, that's fine. But if you want to do like just ignore the last part and give me minimum radius that way, that should be fine as well. Okay? Yes.
Alpha is the whole term, alpha 0.08 or just alpha?
Yeah, so tan alpha is 0.08. So if somebody says super elevation is 0.08, then your tan alpha is 0.08. But again, it's the law of small numbers. So you could say at that small of an angle, alpha and tan alpha will be basically the same. They will be very close to each other. But strictly speaking, when somebody says super elevation is 0.08, that means tangent alpha is 0.08. This is basically how much horizontal. So it's basically 100 feet horizontal for 8 feet vertical. That's what I have. Okay, so 8% grade is 0.08. It represents tan alpha, strictly speaking, even though alpha and tan alpha would be very close to each other at those small values. Questions, comments? Okay. All right. So let's see. Not this. So one more thing about the simple circular curve that we are going to design in this class that we have looked at. There's always going to be simple curve, circular curve with a constant radius. You could have compound curves where it's one simple curve follows another one. And then the spiral curve, those are typically used only for railroads. Okay, those are typically used for railroad design because your trains are much longer and you have to actually provide a transition from the straight segment to a curved segment. So you design that transition using spiral curve. Again, we're not going to design all of that. If you're interested, C422 is your class if you're interested in designing more. But I'm going to stop here. We'll pick up the discussion on side distance in Tuesday's class. Have a great weekend, and I'll see you guys next week. Thank you.